Ladies and gentlemen, welcome back to lesson 21 in group theory. In this lesson, we're going to be talking about the fourth and last isomorphism theorem, also known as the theorem of correspondence. This theorem describes the relation between the subgroups of G that contain N and the subgroups of the quotient group of G by N. In lesson 12, subgroups generated by a subset, we have taken how to draw the lattice of a group. The lattice of a group describes none other than the subgroups of this group. So this is exactly what I've drawn here. On the left-hand side, I've drawn all of the subgroups in between G and N, so basically the subgroups of G that contain N. And on the right-hand side, I have all of the subgroups of the quotient group G by N. We realize here that if we collapse N by itself, we get something that is isomorphic to the identity. So this is essentially the complete lattice of the quotient group G by N. And what this theorem says is that this lattice can be completely read by just reading the lattice of the subgroups of G that contain N. We will get into the official statement and the proof, and then we will provide some examples in the quaternion group and the dihedral group D8. Let's get started. Let's start with the official statement of the theorem. This theorem says that if G is a group and N is a normal subgroup of G, then there is a one-to-one correspondence or a bijection between the subgroups H of G that contain N and the subgroups Hn of Gn. Exactly, this is the relation that I've mentioned in the introduction. The correspondence between the subgroups of G that contain N and the subgroups of Gn. The second result further elaborates on this bijection. If A and B are two subgroups of G, with N a subgroup of A and N a subgroup of B, so basically saying that A and B are two subgroups of G that contain N. Then the first result says that A is a subgroup of B if and only if AN is a subgroup of Bn, which looks intuitive enough. Number two says that if A is a subgroup of B, then the index of A and B is equal to the index of AN in Bn. Number three says that if we take the subgroup generated by AB and we take the quotient of that by N, this is equal exactly to the subgroup generated by the quotient of A by N and the quotient of B by N. Number four, we have that if we take the intersection of AB and we take the quotient of that by N, this is equal to the intersection of the quotient of A by N and the quotient of B by N. Number five says that A is a normal subgroup of the group G if and only if the quotient A by N is a normal subgroup of the quotient G by N. So you can see sort of here, everything is about reducing by N. So let's get started with the proof. The first step in my proof is to prove that there is a correspondence between the subgroups of G and those of G/N. So this is exactly what I'll be constructing. I will define a map, which later I will prove to be a bijection. I call it UN. The subscript here is N, which is the normal subgroup in question. So if I change the choice of N, this map will change based on that N. Define the map UN as follows. And now we need to define the domain and the codomain of this map. The domain of this map is the subgroups H of G such that H contains N. The codomain are all the subgroups of G/N. And the map is defined to be taking H, if you apply UN, it will give you H/N. That is the definition of the map we have provided. And now we want to see that UN is a bijection, so we will define the inverse of un, which takes an element k from the domain of the inverse map and gives you back an element in the image of the inverse map. So the definition here is not explicit like in here. Here we know exactly the definition. It carries h over to h quotient by n. But here we just simply say it carries it to the image of the inverse map un inverse. And based on this definition, we will see that un is a well-defined map that is a bijection as well. The first thing is that un is well-defined. The reason un is well-defined, firstly, is because we would like to see that if we take a subgroup of G containing n, we would like to end up with a subgroup of Gn. So, if H is a subgroup of G containing n, then Hn is a subgroup of Gn. We would like to prove this. Proving this is, first, since the identity is in H, because it's a subgroup, we have that 1n is in Hn, since 1 is in H. So, Hn is not empty. That's the first thing in proving it's a subgroup. The second thing is if H1n, H2n are elements in Hn, we would like to prove that H1n, H2n inverse is also an element in Hn. And this is equal to H1, H2 inverse n. I skipped a step here, which is to use the inverse of cosets. And then I did coset multiplication. So here I combined both coset multiplication and coset inverse in one step. And this is an element, in fact, of Hn. Because we've said that H is a subgroup, so it is closed under operation and inverses, making this an element in H. So we've successfully said that Hn is a subgroup of Gn. So un does map subgroups H of G to subgroups Hn of Gn. So un is well defined as a map. Now we would like to see that the inverse of un is also well defined. Remember that un inverse takes subgroups of the quotient group Gn and gives you subgroups of G that contain n. So this means that if you want to have that un inverse is well defined, we need to see that it takes this to, in fact, a subgroup of G that contains n. So the first thing to prove that anything is subgroup, we need to see it's non-empty. So let K be a subgroup of the quotient group Gn. We have, first of all, that since un of the identity is equal to, by definition of un, 1n, which is equal to n, and n is an element of K because K is a subgroup of Gn. And what is the identity element of the quotient group? It is exactly n. So n, the identity element, is found in K. So because un of 1 is found in K, if we apply un inverse in both sides, we get exactly that un inverse of un of 1 is contained in un inverse of K. But un inverse of un, they cancel out because that's the inverse of that. So it's just 1, the identity, is found in un inverse of k. Deducing from that un inverse of k is non-empty. That is the first step in proving that un inverse of k is a subgroup. The second step, of course, let k1, k2 be two elements in un inverse k. We would like for k1, k2 inverse also to be an element in un inverse k. Because k1 and k2 are elements of these, then k1n and k2n are elements in k. Remember that un inverse contains k1, k2, so if you apply un by taking the cosets of n, it will be inside k. So if you take k1n times k2n inverse, this is equal to k1, k2 inverse, n, equal to the coset k1, k2 inverse. And now this element, this coset here, lies in k because we have assumed k to be a subgroup of the quotient group Gn. So because we have this fact, we have this inclusion here. So if we apply un inverse on both sides, we will get that k1, k2 inverse is an element in un inverse k, thereby proving that un inverse k is a subgroup of G. So this means that un inverse carries subgroups of the quotient group Gn to subgroups of G. But now we need to see more than this. We need to see that it carries to subgroups of G that contain n. Because remember, we're here now. So it has to contain n. Now prove that k contains n. So we prove that if there is an element here, then this element has to be in here. That's sufficient. If n is an element in n, then we can say that the coset nn, which is equal to n because an element in n times an element in n gives an element in n, and n, we said this is the identity of the quotient group. So we've just successfully proven that if n is an element in n, then n is an element in un inverse k. This means that n is a subgroup of un inverse k because n is a subgroup of G. So because un inverse k is a subgroup of G that contains n, then we can say that un inverse of k is an element of this set that we've talked about, subgroups of G that contain n. So we've successfully said that un inverse does map subgroups k of G/n to subgroups H of G containing n, thus proving that un inverse is also well defined. Now that we have proved that un and the inverse map of un are both well defined, it is time to prove that it is a bijection. Disclaimer, I'm not going to prove the whole thing, I'm going to prove half of it. The other half, I will leave it to you as an exercise because it is mostly an exercise in discrete mathematics, in set theory, more than group theory. So we need to prove that, first of all, un of the inverse map of un of k is equal to k for no matter what k. And this I leave to you as an exercise because you can use the property of functions on sets. The second point, however, I will be proving because it demands a little bit of group theory. So this time, un inverse of un of h is equal to h. To prove 2, we will prove the equality of sets by double inclusion. First inclusion, h is included in un inverse un h. This part here requires no group theory, and this is just set theory. I will leave this as an exercise again. The other inclusion, this I will prove. So if k is an element of un inverse unh, then we can apply un on both sides. So apply un here and un there to get un of k is an element of un of h. So now that we have this, we know that un of h is gonna be the quotient h by n. So because it is an element in the quotient h by n, then there exists a small h such that this is a coset of hn. So there exists an h in h such that kn is equal to hn. And if these two cosets are equal, then due to a property of equality of cosets, this means that k is an element in the coset hn, because these two are two representatives of the same coset. So naturally, these two elements are found in the same coset, which is hn. Since n is a subgroup of h and is contained inside h, then hn is contained inside h as well, because h is contained inside h and is contained inside h. So naturally, this coset is contained inside h, and k, because hn is in h, then k is an element in h. So this means that we've successfully proven that if k is in here, then it is in here. So un inverse of un of h is a subset of h, and the second part too is proven. To recap, we have proven that the map that we have defined. To recap, we have just defined un, we've defined un inverse, we have proven that un and un inverse are both well defined, and lastly, we've proven that they are in fact the inverses of each other by saying that the composition of un and un inverse from both sides gives the identity here. Therefore, we have successfully found the bijection, which is the one-to-one correspondence between the subgroups of G that contain n and the subgroups of the quotient group Gn. Now it is time to prove the 5 statements that follow. For the first result, I will be proving only the forward direction and the backward direction because it's very similar. I will leave it to you as an exercise. For the forward direction, I would like to prove that an is a subgroup of bn, knowing that a is a subgroup of b. The first thing to notice is that because a is contained inside b, it is natural to see that a/n is contained in b/n. So if a is an element in a, then because a is a subset of b, a is an element in b. So if an is an element in the quotient group an, then because a is in b, an is an element in the quotient group of bn. So an element here is found in here. And we get that an is a subset of bn. Now it's time to prove that it's not only a subset but a subgroup. We have that an is not empty since n is contained in an. We know that n exists, so it's the identity element of the quotient group an. Next, if a1n, a2n are two elements in an, then if we take a1n times a2n inverse, this is exactly equal to a1, a2 inverse n. And this here is an element in A because A is a subgroup of B. So this is an an. Thus proving the forward direction of the first result. The backwards again left to you as an exercise. Okay, let us now prove the second result, which says that the index of A and B is equal to the index of an and bn. Remember that the index counts the number of cosets. So this is the number of cosets of A in B, and this is the number of cosets of an in bn. But this proof is very, very straightforward. The reason is because we've already seen that there is a bijection between the subgroups of G containing n and the subgroups of G slash n. Okay? And clearly, B slash n, A slash n are both subgroups of G slash n because we know A and B are both subgroups of G containing n. We've already seen this bijection. But now we want to see that if we take a coset of A and B, we're going to get a coset of an and bn. We're not going to get something that's not a coset of an and bn. And the reason this is true is because of the first result that we have proven, saying that if A is a subgroup of B, then an is a subgroup of bn. Also, use first result to say that an is a subgroup of bn, therefore ensuring that any coset of A and B, because of the bijection here, is mapped to a unique coset of an in bn, completing the proof of the second result. The proof of the third result will not be using the double inclusion that we usually use to prove equality of sets. What we're going to do is we're going to see what happens here. We're going to see what happens here, and we're going to say that these two things are equivalent. So it's an if and only if, immediately giving us the equality. So let us start with what happens here. Okay? So let me just put up a nice division here in the board. And on the right-hand side, I will write down what happens with A slash n, B slash n. So if I have an element Gn in A slash n, B slash n, remember here, this is a subgroup generated by cosets. So this has to be a coset. So this means that Gn is a product of some cosets from A, some cosets from B. So it's going to be maybe a possibility, like for example, A1n, B1n, A2n, B2n, A3n, B3n, and so on until AKN, BKN. But that is just a possibility. There could be other possibilities such that we could have the same exact thing except that at the end of the product, we could have BK first and then AK. That's another different possibility that we could have. The point here is that no matter which possibility we will choose, we will get the similar result. So without loss of generality, we will suppose that this is what it will give us. Okay? But just keep in mind, this is not the only possibility that Gn could be. But let's say for the sake of our argument that it is this. Okay? So if that's true, and this is equal to, the right-hand side is equal to A1, B1, A2, B2, all the way to AK, BK, N. So what I did here, simply coset multiplication, A1, B1, A1N, B1N is equal to A1, B1N, and I just combine all of the elements of A and B together. So now I have that this coset is equal to that coset. And by definition of coset equality, this gives me that G inverse times all of that is an element in N. Okay? So G1 inverse times all of that is equal to N for some N. Okay, now we have finished the right-hand side. Let's do the left-hand side now. The left-hand side being A comma B, quotient with N. Okay, let's take an element of that thing here. Okay, now if Gn is an element in this quotient, this means that we will write down all of the products of A and B, and then we will take the quotient by N. So we'll take the coset of the products of A and B by N. One possibility for the coset is to have A1, B1, A2, B2, all the way to AK, BK, and take that coset with N. Of course, again, there are other possibilities, but for our argument, without loss of generality, we will assume that this is the possibility that we have. So we have again that Gn is equal to this coset here. But this means exactly by coset equality that G inverse A1, B1, AK, BK is an element in N. Therefore, G1 inverse times A1, B1, AK, BK is equal to N for some N and N. Okay, so we've just reached the same conclusion whether we started here or we started there. This means that these two statements are equivalent. There is an if and only if. And this proves directly the equality of the sets, completing the proof of the third result. If you're a bit lost on the intuition, don't worry, I got a nice analogy for you. So let's talk modulo here. Let's talk about modulo 2, for example. So what do we have modulo 2? We have even numbers and odd numbers. So the analogy here is that the left-hand side, what we're doing is we are adding two numbers, and then we're taking the quotient modulo 2. So we are adding two numbers, let's say 3 and 5. And then after doing the addition, we get the quotient modulo 2, so we see if it's an even or an odd number. This is, of course, an even number, so it is 0 bar. This is the left-hand side. In the right-hand side, we first do the quotient and then we add. So it's 3 bar plus 5 bar. That's the difference. So 3 bar here is 1 bar and 5 bar is 1 bar. And an odd number plus an odd number gives an even number. So this is equal to 0 bar. And you can see that both give the same result. This is exactly the analogy that can help you understand this part of the theorem. The proof of this result will be by double inclusion. So the first inclusion being this is contained in that. So let an element here, a coset Gn, that lies in A intersecting B, quotienting with N. This means that G is an element of the intersection of A and B. This means that Gn is an element in the quotient group An, and Gn is an element in the quotient group Bn. And therefore, Gn is an element in the intersection of an and bn, therefore completing the forward inclusion. A intersecting b, quotienting with n, is included in the intersection of an and bn. Now, backward inclusion, let Gn be an element in the intersection of an and bn. This means that Gn is equal to an for some a in A, and Gn is equal to Bn for some B in B. So because we have that Gn is equal to An and equal to Bn, we can say that An is equal to Bn. Okay, and since we have that, by coset equality, we can say that A inverse times B is an element in N. But remember that N is a subgroup of both A and B. So that means this element is in A, and this element is in B as well. So, in particular, we have that because it's an element in N, by coset equality, we have that A inverse Bn is equal exactly to the coset N. And now, if you look at Gn, well, Gn, we've said it's equal to An. And we can replace now N by this, A times A inverse Bn. So all of this is some element A in A. A times A inverse B is some element in A, and we know that A is in A, and that A inverse B is not only in A, but also in B because of this. So this means that B necessarily, because all of this is an element in A, this forces B to be an element in A. But we know that B, by supposition, is an element in B. It's both in A and B, so B is an element in the intersection of A and B. So, if B is in the intersection and Gn is equal to Bn, this here is an element in the quotient A intersecting B by n. Simply taking an element from the intersection, taking the coset of that with n, yields an element in A intersect B by n, giving us that this is contained in that, completing the equality, and we're done. To prove the fifth result, I will prove the forward and the backward direction. So let An be a coset, an element of An, and Gn be an element in Gn. I already know that A is a subgroup of G if and only if An is a subgroup of Gn. So all that is left is to prove that it's a normal subgroup, so that it's closed under conjugates. So if I take an element in my subgroup and I take an element in my group, I would like to see that the conjugate is still in my subgroup. So we have our element An multiplied by Gn on the left and by Gn inverse on the right. This equals to Gag inverse n, and this is an element in An because this is an element in A, because A is supposed to be a normal subgroup of G, therefore closed under conjugates. So forward direction is complete, and An is a normal subgroup of Gn. To prove the backward direction, we will also do it the same way. Let A be an element in A and G be an element in G. we would like to see what happens when we take GAG inverse. But before that, we know that this is a normal subgroup in that. So AN, GN, GN inverse. We already know that this is equal to A1N for some A1 in A. We know this is true because we suppose this is true, that it is closed under conjugate. So we can say this statement is true. And this is if and only if GAG inverse N is equal to A1N. So I just use coset multiplication on the left-hand side. And this is if and only if. Because these two cosets are equal, I will use coset equality to say this is if and only if A1 inverse times whatever this is an element in N. But N is a subgroup of A. So this all is an element in A. Well, what about this element? You can see here, this here is an element in A because A is a subgroup. And because the whole thing is an element in A, this forces this as well to be an element in A. So GAG inverse is also an element in A, making A closed under conjugates, meaning that A is a normal subgroup of G, completing the fifth and the final proof in this big important theorem. Let us now look at two examples using this theorem. For the two examples, I have the lattice of the subgroups, and here I will show you, for example, the quaternion group Q8. Recall that the quaternion group is the group of roots of unity. So we have the three roots of unity, I, J, and K, and you can see that in Q8, the subgroups that are included in are the subgroups generated by I. These are I square, I3, I4, and I square is equal to -1, I3 is -I, and I4 is equal to 1. Same with J, and the same with K. And you can see that the subgroup generated by -1, which is -1, -1 squared, and that is equal to 1. This subgroup is included in all three subgroups, and that's why we have the lines like that. And at the end there, we have the trivial subgroup, which just contains the identity 1, which is contained in all of the subgroups above. So whatever subgroup above contains a subgroup below if there's a line connecting these two subgroups. So we will use the theorem now to construct the lattice of Q8 when we take it the quotient with -1. Since the subgroup generated by -1 is a normal subgroup in Q8, and -1 is contained in all three subgroups, I, J, and K, we can construct the lattice of the subgroups of Q8 quotient with -1. This gives us the same exact lattice, the same exact structure, just reduced by -1. And -1 is collapsed onto the identity. So this is isomorphic to the identity, containing only one element. So if you look at both diagrams, you can see we have collapsed everything modulo -1. Let us now have a look at another example, which is D8, the dihedral group of a square. In D8, we have the lattice as such. We have the subgroup generated by S and R2, which is S squared, R2, R4, but R4 and S squared are just 1. And we have also SR2 and R2S. but R2S is SR minus 2, which is SR2. So all of this is the same. So these are the elements in SR2. That is just an example of how you list the subgroup generated by these two elements. SR3R2 is another one, and the one generated by R is another one. And you can see that all of these contain the subgroup generated by R2. On the left side, you see that this subgroup contains these two subgroups, and this subgroup contains these two subgroups. However, these two subgroups are not contained by this one, and vice versa. So when we're thinking about reducing this lattice, collapsing this lattice, we would like to first look at a normal subgroup on which we will do the collapsing. The normal subgroup is going to be the subgroup generated by R2. And R2 is going to branch out from these four over here. So these four are not going to be included in our new lattice. In our new lattice, we will only consider the subgroups that contain this subgroup. The subgroups that contain this subgroup are this, 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 and that. Therefore, this is the structure of my new lattice when I reduce everything by R2. So using the correspondence theorem, I am confidently able to draw this lattice and tell you there is a one-to-one correspondence between each element in this lattice here and each element in the lattice here. And the one-to-one correspondence is simply taking this element here, for example, giving you the coset with R2. And the inverse map, of course, is well defined as we have already said. So this has been the end of this lesson. So this marks the end of this lesson. If you've enjoyed, drop a like, subscribe, and share with anyone who'd be interested. I will be dropping more group theory content soon. Have a nice day, and bye.